What if the roots to our quadratic equation were imaginary or complex? Fortunately for us, it does not change the process that we will use. The zero product property still guarantees us the ability to write those factors and multiply them out. Also to note, though, you might remember from our work with the complex conjugate, the conjugate root theorem, that the complex roots will always be conjugates of one another. So whether it's just an imaginary part, like the example you see here, negative 7i and 7i, or it's a complex number that has a real part and an imaginary part, it's not going to change the process that we use. It might make the mathematics and the mental gymnastics a little bit tougher to get through, but it doesn't change the fact that we are going to set up those factors, we're going to multiply them out, we're going to simplify what we can, and we're going to create a quadratic equation. And because these roots are conjugates of one another, we should anticipate when we do our multiplication a lot of simplifying, and we should be on the lookout for I squareds that we can turn into negative 1. So taking a look at this first example where they just have the conjugates of two imaginary parts, we're going to write our two factors. And again, we're going to jump right to the factors. And that's the binomial that would give us negative 7i as a solution equaling 0. And here's the one that would give us 7i as the solution. Now, this isn't technically wrong. Like, this is a correct answer. That's a quadratic equation that has those roots. But when we're thinking of a quadratic equation, we really are thinking of it in standard form. So we're going to multiply this out and see what we can simplify. So we're going to say x times the binomial in the second parenthesis. So that gives us x squared minus 7ix. And then we're going to see 7i times that second binomial, which is going to create a plus 7ix minus 49i squared. And all of that is equal to 0. Simplifying what we can, these two are opposites of one another. I squared is equal to negative 1. So that changes that last term, negative 1 times negative 49, into plus 49 equaling 0. And again, this would be a perfect opportunity to check it with the square root method, where we have x squared is equal to negative 49. We take the square root of both sides, and we're left with positive or negative 7i, which is exactly what we would have expected. So again, 2 lessons ago, we were going this direction, but we weren't doing any of this. We were going right from here all the way up to the solutions. But the zero product property and the principle of working backwards allows us to create the equation from scratch instead of trying to create that equation from scratch maybe from down there. All right, what if our solution is a full complex number with a real part and an imaginary part? Well, you guessed it. We're going to do this one the exact same way that we did the others. Minus our first factor, minus our first solution, and then minus our second solution. All of that is equal to 0. We're going to run that minus sign through both of those expressions so that we can clear out that extra set of parentheses that we don't need. And again, I mentioned this in a previous video, we could go difference of squares factorization here where we have this factor minus that one and plus that one. I don't want to go through all of that. I know that my next step that will get me where I need to go is to do a multiplication of the first times the second expression. Is it going to take me a little bit of time? Sure, but it doesn't change the fact that I know it's going to work. So let's go x times the second parentheses, x squared minus x plus 3ix. And again, we're going to anticipate a lot of cancellations here. So you want to be very careful about how you write it. And if you do this and you don't get a lot of cancellations, that's a pretty good sign that you did something wrong. Negative 1 times the second parentheses is just going to change everybody's signs. And negative 3i times the second parentheses, this is where we're going to see a lot of our cancellation factors. Plus 3i minus 9i squared. Starting first with some of the cancellations, I see 3ix and negative 3ix right out of the gate, and negative 3i and 3i right out of the gate, which is great because I don't write quadratic equations that have complex parts in them. That shouldn't be really part of our solution. We're not worried about this one because we know what's going to happen to him, but we are a little bit concerned about the rest of them, and we want to make sure they all go away. We're left with the x squared, and then minus 2x for these two. We have this 1 here, but we also have 9i squared. I squared is -1. -1 times -9 is +9. That 9 plus that 1 makes a total of 10, and all of that has to equal 0. So a matter of writing a quadratic equation that has complex roots. Again, the complex roots must be conjugates of one another. They're not going to come as a single solution. They will come in pairs. So even if an example says you have one root at 1 plus 3i, you know the other one has to be at 1 minus 3i, even if they don't tell you that. We know we can do that. We know we can go through the same kind of thinking, even though that we never factored like that. We never factored to create a polynomial or a multiplication that looked like that. That's not our concern. Our concern is, can we create something that is guaranteed to be a solution? And if you can write something that has that solution, multiplying it all out allows you to get to a simplified point where you can see a quadratic equation that we could graph. We graph this, we're not expecting any roots. We're not expecting any roots on the real number system. Here's our roots. And we would see the same thing back here. So strategy doesn't change with complex numbers. The process is still the same. You just have some extra simplifying that you need to worry about before you're able to write the finished version of the equation.